So the next idea is of a standard normal variate. So let me quickly define what a standard normal variate is. So it's often written with a small z or a small z. So a z is basically a normal, is a Gaussian distributed random variable with a mean of 0 and 1, right? Now, this is what is called, so if you have a random variable like z or z with a mean of, with a mean of 0 and a variance of 1, that is called a standard normal variate. Okay, we'll see why it's called standard and why it's useful. Okay, so this is the first part. Second part is, let's assume I'm given a random variable x, right, which is Gaussian with a mean of mu and a variance of sigma square. Let okay, and let's assume I sampled a bunch of points from this distribution. So let's assume this x is, let's say, petal length, and let's assume I have 50 petal lengths of let's say setters of flower, right? So I have my x1, x2, so on and so forth, x50. Now all these are observations of this random variable. This random variable can take multiple values, right? So let's assume these are the 50 values that I got. Now, given these observations of this random variable, I can standardize these values. I can apply a transformation called standardization. Standardization. So, of course, these random variables have a mean of mu and a variance of sigma square. So the way we can simply standardize is, for every variable xi here, let me define a new variable xi dash such that xi dash equals to xi minus mean by standard deviation. So when I do this, I can easily prove it to you that xi dash, if x is distributed, so if xi's come from a normal distribution with mean mu and variance sigma square, my xi dash will come from n01, or my xi dash is basically a standard normal variate. A standard normal variate. In other words, given any distribution, given any random variable with a mean mu and a variance sigma square, I can convert into my standard normal variate by basically subtracting the values of x by basically subtracting mu from values of x and dividing it by sigma. So as soon as you do this, you can say that z is basically a random, it's basically a random variable with a distribution of n01. Such an operation is called standardization of your data. So for example, just going back to this, if you're given 50 values of petal length, you can standardize them by just subtracting the mean of all of these values and dividing it by standard deviation. So this type of transformation of your variable, here you're transforming your 50 observations into 50 other observations, right? For each I equals to 1, 2, so on and so forth, 50. So these are your xi's are your actual observations, and you're transforming them to xi dashes, such that xi dash has a mean of 0 and a variance of, or a standard deviation of 1, right? Having said this, you might ask, okay, why are we even normalizing, or why are we standardizing this data? What is the point of standardizing? So given any random variable x with any mean and sigma, the moment I standardize it, I know exactly how it's, I know exactly. So the moment I standardize it, I know that between 0 and 1, or sorry, between 0 and 1 exactly, because after I've standardized my data, I know that 34% of my data lies here. So if you tell me that x is a normal distributed random variable with a mean of mu and sigma square, if I just simply apply my standardization operation, I know that whatever values of z that I get after normalization, sorry, after standardization, I know that about 62% of my points lie between -1 and 1. So in this example, I know that 68%, I know that 68% of my xi's lie between -1 and 1. By just, so whatever the value of mu and sigma is, doesn't matter, right? And I also know that 95% of my xi dashes lie between -2 and 2, right? So standardization is a good method wherein I can transform any random variable with any mean and variance into a standard form, which is mean of 0 and a standard deviation or variance of 1. right? So this is called standardization. This is simply to basically say, given any random variable, I want to convert it into standard format, because once I convert it into the standard format, I know exactly that the bunch of properties of a standard normal variate like z or z here that I can quickly understand and interpret.